Welcome students to this lecture of the series Introduction to Algorithms. So we have seen asymptotic notations wherein we saw big O, omega and theta notations. So in today's lecture we are going to see some operations and properties of asymptotic notations that will be helpful when we are calculating the time complexities of algorithm. Okay. So we'll start with some operations means when we will be having your asymptotic notations in equations, what do they imply? You should be knowing that when your asymptotic notations exist on the left hand side of the equation, what do they mean? When they exist in the right side of the equation, what do they mean? And when they exist in between an equation, what do they imply? Okay. So we will be looking at these three cases. So the first case is pretty simple. So if your asymptotic notation, that is big O is here, is on the right hand side of the equation, what does it mean? So we have already seen that it simply means your set membership. What does that mean? That means that n belongs to order of n cube. And you know what order of n cube means, that there will be some constant c multiplied by n cube that will be greater than n for all n0, okay? N greater than n0. So this we have seen whenever your asymptotic notation exists on the right hand side of the equation, it simply means set membership, means this belongs to the functions of, means this belongs to the order n cube, okay? Now in second case, we can have something like this. Say we have 5n square plus n plus 2, okay? So what we can do is that we can write this equation as 5n square plus theta of n. So you can see here what we have done is that we have written your asymptotic notation. It comes in between your equation. Of course, it's on the right hand side, but it is in between the equation. So what does it mean? It means that we want to replace this with an anonymous function. Okay, we are replacing this with an anonymous function, this. Fine. Means we are only interested in this higher order, that is 5n square. We are not interested in the lower order terms, but because they exist there, because they are, we cannot just simply replace it. We cannot write 5n square is equal to 5n square plus n plus 2 is equal to 5n square. What we do, we replace this n plus 2 as theta of n. So what does that mean? That means we have an anonymous function f of n which will belong to theta of n. So here that f of n is n plus 2, and we know that n plus 2 is theta n, that is it is tight bound is n, okay? So that is the second way that we can write your asymptotic notation. And finally, we will see what will happen if your asymptotic notation is on the left hand side of your equation. So for that, say for example we have 2n square plus theta of n is equal to theta of n square, okay? So what does it mean? So because we have seen something similar over here, so you can comprehend what the left hand side means. We are taking 2n square and then we are taking an anonymous function of order n here, but we are showing that it equals to theta of n square. It means that if we take two functions f of n that belongs to theta of n, there will definitely exist a g of n that will belong to theta of n square for all n. So what we are trying to do here is that we want to show, we have this equation 2n square plus something which is of order n. So we replace that something with this theta of n, we replace it with an anonymous function. We know it is there, but we are not concerned about it. And we are equating it with theta of n square. So what does that mean? Mean for any f of n that you take in theta of n, there will be a g of n which will belong to theta n square for all n. Okay. So these were some operations of asymptotic notations. Now we will see some properties pertaining to asymptotic notation which will be helpful for other topics. So while discussing the properties of asymptotic notation, we'll begin with some general properties. So the first one, so in general properties, if we have f of n which is equal to order of g of n, okay. So what will happen if we multiply some value with f of n? What will happen to the order of g of n? Okay. So a multiplied by f of n will still be of the order g of n. This is the first property. So we will see it with the help of an example. So for example, say we have f of n which is equal to 2n square plus 5. Okay. So it is, we'll see the upper bound, it is order of n square, you know that. Okay. So now what we'll do is that we'll multiply f of n 4 times. Okay. So 4 times multiply f of n will be equal to, if we multiply it by 4, it will be 8n square plus 20. And you can see that it is still of the order n square. Fine. So that is the first property. If we have f of n which is of the order g of n and we multiply f of n with some constant, it will still remain of the same order, means the order will not change. Now this general property applies to all three of the notations, means all three bounds, the lower bound, the upper bound and the tight bounds. That means this applies to big O, this applies to omega, and this also applies to your theta notation. Fine. So now we will see another property. So the next property that we are going to see is the reflexive property. So if we are given f of n, okay. If we have f of n, so f of n will always be of the order f of n. Okay. So we will see it with the help of an example. Say we have f of n which is equal to n square. Okay. So we know it is equal to order of n square. Fine. So we can set any function as its own upper bound. Fine. Because we are talking about upper bound, we are not talking about the tight bound. Fine. So for upper bound, we have a reflexive property that if we have f of n, then f of n is equal to order of f of n. Fine. And this also applies to your lower bound. Lower bound, that is your omega. So it does not apply to your theta, because we cannot simply write, if we have say f of n square plus something, we cannot write it as to be theta of n square. So at that time you have to see if we have a tight bound there. It may apply in some cases but not always. But for your upper bound, that is big O, and your lower bound, that is omega, we have reflexive property that if we have a function f of n, it is equal to order of f of n, or it is equal to omega f of n. Next property that we are going to look at is the transitive property. So again, we will take a function f of n, and we'll also take another function g of n. We'll take two separate functions and we'll see if transitivity applies to them. So if we have given, we have f of n which is order of g of n. Fine. And we have g of n which is order of h of n. Two functions here, f of n and g of n. Your f of n is order of g of n, and your g of n is your order of h of n. Okay. So what we can say from this, we can say it will imply that your f of n is order of h of n. So we have applied transitivity here. Means if f of n is order of g of n and g of n is itself order of h of n. So we have replaced this g of n with h of n. Okay. So we'll see an example to see what it means and if it is right. Okay. So for example, f of n is n, okay, g of n is n square, and h of n is n cube. So you know we can write f of n is order of g of n. Yes, it is. We can say that it is g of n is n square. We can say that upper bound for n is your n square. Also, we can say that your g of n is order of h of n, which is equal to order of n cube. Yes, we can write, because g of n is your n square and n square is order of n cube, the upper limit. Okay. So from these two, using transitivity property, what we can say is that f of n is order of h of n, means it will be order of n cube. Yes, it is true. So while studying the time and space complexities and growth of functions, I have shown you that whenever we have to calculate the upper bound, we can go anywhere. We can go, if we have n, we can go to n log n, we can go to n square, we can go to n cube, we can go to 2 raised power n. So those are anything that is above your function, that will serve as the upper bound. So here f of n is order of n cube. So it proves our transitivity, means if f of n is order of g of n and g of n is itself order of h of n, then we can say your f of n is also the order of h of n. Fine. So now we'll move on to our next property. So it's the fourth property, the symmetric property. So your symmetric property applies only to your tight bound, that is your theta notation. So if we have f of n, which is theta of g of n, okay, then your g of n is theta of f of n. So you can see why I said that it applies only to your tight notation, that's theta notation. Because it is tight bound, then only we can say that g of n is f of n. Had it been the upper bound, like we saw in the previous example where f of n was n and your order of g of n was n square. So it was true, but n square is not order of n. Okay. So for tight bound, because it's a tight bound, it can be reversed. Means if f of n is theta g of n, then we can say that your g of n is also theta of f of n. So you should remember that your symmetric property applies only to your tight bound, that is theta notation, and not to your upper or lower bound. So we'll see an example. If f of n is equal to n square, okay, and your g of n, it's also equal to n square. So we can say that your f of n is theta of g of n, and because f of n will be theta of n square, which is true, fine. And we can also say that g of n is equal to theta of f of n. Okay, so what is f of n here? N square. So it will be theta of n square. Fine. So that is your symmetric property. Moving on, we'll see our next property, transpose symmetric. what happens in transpose symmetric is that if we are given a function f of n which is of the order g of n. So we have seen that f of n will be a function if we plot it, and g of n will be above it, multiplied by some constant c. So if we look at it that way, so this is your f of n, and this is your c multiplied g of n. Okay. So you can see that f of n is order of your g of n. But at the same time, if you look at this in the opposite way, you can see that f of n will be the lower bound for your g of n. Then we can say that g of n so in case of theta, when f of n is theta of g of n, we can say that g of n is theta of f of n, fine. But when it comes to the upper bound, when g of n is upper bound for f of n, then f of n will be lower bound for g of n. So we can say that g of n is omega f of n, fine. So we'll look at it with the help of an example. Say we have f of n which is equal to n, and we have g of n which is equal to n square, fine. So f of n is order of n square g of n, okay. At the same time, g of n is, so the lower bound for n square will be n, okay. So this is the one property. Another property that we are going to look at is if we sum two functions, what will happen to their time complexities, and finally we will see that if we multiply two functions, what will happen to their time complexities. So if we have f of n which is equal to order of g of n, fine, and then we are having a separate function d of n which is of the order of e of n. These are two separate things. F of n is order of g of n, and then there is some other function d of n which is of the order of e of n. Now what will happen if we add these two? If we add f of n plus d of n, okay, what will be the order of that? So the order will be maximum of g of n or e of n. So if we add f of n and d of n, their order will be whichever is greater among these two, g of n or e of n, okay. So we will see an example. If f of n is equal to n and d of n is equal to n square, okay. So what is f of n? It is order of n, and what's d of n? It's order of n square, fine. Now if we add these two, so f of n plus d of n will be equal to n plus n square, okay. So what's the order of this? It is order of n square, means whichever is the maximum among these two. We are seeing the maximum of g of n and e of n. So the maximum is here e of n, that is n square, so we are writing it as an order of n square, fine. So now we will take the same scenario, but instead of adding them, what we will be doing is that we will be multiplying them, okay. So now the last property we are going to see is that if we are having two functions f of n and d of n, f of n is order of g of n and d of n is order of e of n. So what will be f of n multiplied by d of n, okay? What will be the order of this new function? It will be order of g of n multiplied by e of n. So we'll take same example as the previous one. If f of n is equal to n and d of n is equal to n square. Okay, so f of n was the order n, and this is order n square. So what will happen if we multiply f of n and d of n? So f of n multiplied by d of n will be equal to n multiplied by n square, which will be equal to n cube. Okay, so it is order of n cube. And how do you get order of n cube? When you multiply these two, n square into n, that is your n cube. Fine. So this finishes the properties of your asymptotic notations. And before winding up these asymptotic notations, there is one big confusion that exists among students after studying your asymptotic notations. We oftentimes confuse your upper bound, lower bound, and your average or tight bound with the best case, worst case, and average case complexity, which is not the case. Okay, so we'll be winding up this lecture with best, worst, and average case scenarios, and we'll be seeing that how they are different from your upper, lower, and tight bounds. Means they don't always imply, and you should not confuse best, worst, and average case scenarios with your asymptotic notations. Means you will say that the big O is the best and the omega is worst and theta is average. That is not the case. Okay, so we will see it with an example of linear search. So if we have, say, an array of values, say 4, 6, 12, 4, 2, 10, okay? So I'll write 14 here so that you don't confuse it with the starting 4. So if we have these values and we want to search, we want to have a linear search over here, what can be the scenarios? Okay, the first one will be your best case. The best case scenario implies that whatever key value that you are looking for is present at the first location, at the first index. Say if I am looking for 4, okay, so where is the 4? 4 is present at the first location. So your best case time complexity, I'll represent it by TB, is of the order 1. Means in best case, what will happen? That your key element will always be present at the first index. So it will be of the constant time, that is 1. So in second case, we'll see the worst case. In worst case, we can have two scenarios. One is that the element that you are looking for is not present in your list. And the second is that it is present but at the last, at the end. Say if we are looking for the value 10, okay. So if you are looking for the value 10, you have to go to the entire length of your list. Or say I am looking for value 15. In that case as well, you have to search through the entire list. Okay. So in both cases, if the element is present at the end or the element is not present, you have to. You are talking about the worst case. Means your algorithm is scanning all of the elements. All comparisons are made. So in that case, your worst will be n. So n here is the size. So I can write here as 1, 2, 3, 4, 5, 6. I can write 6 because there are 6 elements, but we are not talking about this thing in general. We are talking about linear search in general. Therefore, I am saying that worst case scenario is n. Okay. Now the third case is your average case. So how do you calculate average case? So average case is here calculated by all possible cases divided by number of cases. So what are all possible cases? All possible cases are, first, all possible cases 1 means the element will be present at the first location. The second possible case is that it will be present at second. Then you have to make 1 plus 2 comparisons. Then the third is that it will be at third, so you have to make 3 comparisons. Then it will be at fourth, so on up to n. So these are all possible cases that can happen in your linear search. And total number of cases is how much? It is n. Okay. So if we add this, these are n natural numbers, it will be n into n plus 1 divided by 2 and whole divided by this n. Okay. So this n and n get cancelled. Your average case is n plus 1 divided by 2. So your TA will be of the order n plus 1 divided by 2. Or I will not write order here, I'll simply write it, your average case will be n plus 1 divided by 2. Okay. So you understood the best case, worst case and average case. Okay. So now let us clear it out that how it is different or how it relates to your asymptotic notations. So what we can write is that your best case is of the order of 1. Yes, it is of the order of 1. It is omega 1. Yes, that is right. And it is theta 1. Fine. Same way we can write for your worst case. So your worst case is of the order n, omega n and theta n. Fine. Now if we take average case, here the highest power is 1, that is n. So it is of the order n, or it is of omega n, lower bound, or tight bound n. So now you can see that upper limit means big O, lower that is omega, and the tight that is theta does not mean best, worst and average case. We can have all three for the best cases, we can have all three for the worst cases, and we can have all three for your average cases. So now we will see another example that is of a binary search tree, and we will try to see its best and its worst case scenario. Okay. So if we have I will make a small binary search tree over here. So I have drawn a height balanced tree over here. So we know for height balanced tree, the height is given by your log n. So this height is of log n. So what can be the best case here? TB I'll write. So the best case scenario will be the element, the key element that you are searching for your binary search tree will be present at the root. Okay. So the best case is that it will be present at the root, and what will be the time complexity for it? It will be order 1. Okay. So you can write it as big O1, you can write it as omega 1, or you can write it as theta 1. So the best case, if we're talking about best case, it will be present at the root, and it will be a constant time, that is 1. So what will be the worst case here? Worst case scenario will be that your element will be present at the leaf node, or it will not be present in the binary search tree. In both cases, you have to traverse up to the leaf node. Okay. So we have seen the height is your log n. So at least it has to go log n. Fine. So this is the best case that is constant 1, and we have the worst case, that is the height of your height balanced tree, that is your log n. There can be another scenario in your binary search tree where if you have a skewed tree, means this is a height balanced tree, we can have same binary tree in this manner. We can have the highest value, that is 65, then we can have 60, then we can have 55, then 50, then we have 35, then we have 30, and finally we have 20. So this is also a binary search tree, but it is a skewed binary search tree. So here the height will be n, so the worst case will be n. Fine. So the whole idea behind telling you about the best, worst and average cases and giving you these two examples is twofold. One is that you should understand what it means and how it is calculated, your best, average and worst case. The second is the very important concept, that is you should not confuse it with the upper limit, that is big O, the lower limit, that is omega, and the tight bound, that is your theta. Okay. So that finishes our this lecture, and in today's lecture we saw some operations on your asymptotic notation. Then we saw the properties on of asymptotic notations. We saw general properties, we saw reflexive, we saw symmetric, we saw transitive, and finally we discussed about the best, worst and the average cases, and we saw how they are different from your asymptotic notations. So I hope to see you in next lecture. Till then, goodbye.